Hi everyone, and welcome back to Graph Theory Visualized. In this chapter, we will be exploring the concept of degree sequences, the Havel-Hakimi algorithm. As mathematicians, we like to represent things in other ways, mostly as it can lead to new approaches to problems we're trying to solve. And to be honest, the alternative representation can lead to interesting problems of their own. Also, as mathematicians, we naturally love numbers, particularly in ordered form. This is the motivation for degree sequences for graphs. We can represent graphs by the degrees of all the vertices given. We can represent it through a sequence of numbers known as degree sequences. Note that not all sequences of numbers have graph equivalents. For example, the corollary of the first theorem of graph theory that we explored in the last chapter is that no graph has an odd number of vertices with odd degrees. See the following sequence. Is there a way we can determine if a sequence of numbers has a graph equivalent? For this predicament, we will use the Havel-Hakimi algorithm. The theorem statement of the Havel-Hakimi algorithm goes as follows. Given a non-increasing sequence of non-negative numbers, d sub 1, d sub 2, all the way to d sub n, and given that the first number is less than or equal to 1, the sequence is graphical, if and only if the subsequent sequence is also graphical. In other words, given a sequence of numbers, we subtract all numbers by 1, and we remove the first number in the sequence. This procedure makes drawing a graph much easier. We won't cover the full proof in this video, but I can give a brief outline of the proof for the direct implication. The converse proof is more lengthy, and in good old math fashion, left as an exercise to the reader, but I encourage you to research it further. Now for the proof. First, we assume that the original sequence is graphical. This means that there is a graph with the following degrees. Since we can construct a graph from G, we can construct a new graph G' by constructing the following. Finally, we get a new sequence from the following graph. Therefore, if the original degree sequence is graphical, then so are also the subsequent sequences produced by the Havel-Hakimi algorithm. In this chapter, we explore the concept of degree sequences and the Havel-Hakimi algorithm. There's an interactive section associated with applying the Havel-Hakimi algorithm to a sequence of numbers. In the next section, we'll be looking at the concept of graph isomorphism, and how we can determine if graphs are isomorphic to each other. I hope you learned something new about graphs in this section. Till next time.